Hey BCAM, this video is going to be on LeChatelier's principle. Okay, LeChatelier's principle, which is in your notes here. I'm not sure which page it is, but you guys can find it in there. I just kind of got a big chart here. LeChatelier's principle is just saying, okay, we have a system at equilibrium, and it's saying what happens if there's some kind of stress applied to that system. You know, something's added to it, something's removed. We change the temperature. Okay, it's usually having to do with changing the concentration of something, changing the temperature, or changing the pressure. Those three things are usually what we deal with, okay? Concentration change in one of these things, a pressure change, a temperature change. So here is our equilibrium system. Here's our equilibrium system. Notice it's giving us an enthalpy change. This reaction is exothermic. That always means it's exothermic in the forward direction. That means it's endothermic in the reverse direction, okay? And there's our K value, big K value, okay? 3,800, no, 38,000, sorry, would be our K value from there, 3.8 times 10 to the fourth. So LeChatelier's principle says that if a change is imposed on a system, so an equilibrium system, if we change something, the position of the equilibrium will shift in a direction that tends to reduce that change. So it tries to counteract that change. Okay, it tries to counteract it. So most of these are fairly easy to figure out. A couple of them get a little bit harder as we go through here. So first thing, if we increase the concentration, the molarity of N2, increase this concentration right here. So if we add more N2 to this system, the system always wants to shift until it gets to this. It wants to be at this. It wants to be at this equilibrium constant. Remember, products over reactants. Well, if we add some N2, that's going to increase how much N2 we have, which means it's going to increase our Q value or K value at that point in time. It's got to shift till it gets to K. So the reaction will always, or the equilibrium will always shift to use that up. So if we increase N2, that's going to cause an increase in N2 initially. Well, what will happen is the equilibrium will shift to the right to use up some of that N2. Always wants to counteract it. So if we add this, it's going to shift right to use some of it up. It might not use all of it up that we added, but it's going to use some of it up. Well, if this shifts to the right, that means this is going to go down, and this is going to go up. That concentration will go down, that concentration will go up. Now, the effect on our K value is nothing once everything settles out. It will always get back to that K value in this case when we change the concentration. So K value will be the same as it was before. It'll stay at that value. Okay, now for a second it would not, but then it would shift until we get back to that ratio. All right, if we increase the concentration of H2, so if we increase this concentration, increase that concentration, again, the equilibrium is going to shift to try and use some of that up. So the reaction has to shift to the right to try and use some of that H2 up. So we're going to have an increased H2 is what we're adding. The equilibrium will shift, The equilibrium will shift to the right to try and use some of that H2 up. As it shifts to the right, that means there's going to be an increase in that and a decrease in that until we get back to that K value. Until we get back to that ratio of this over this equaling 38,000. So N2 is going to go down, and H3 will increase, but our K value will stay the same. So changes in concentration, I think, are pretty easy. Keep going down here. An increase in NH3. So again, our equilibrium is N2 plus 3H2 from 2NH3. So if we would increase how much NH3 is there, if we increase that value, okay, equilibrium is going to shift left. It's going to shift left, which will cause an increase in H2 and an increase in N2. So we basically have increased everything, but again, our K value does not change in that case. K value doesn't change. If we decrease one of these things, okay, I may not do all of these decrease ones because it ends up being pretty similar, but again, LeChatelier's principle says it tries to counteract the change, So if we would have a decrease in N2, if we start removing this, so if somehow we remove N2 from this equilibrium system, the equilibrium has to shift to try and replace some of that N2 to stay at that K value. Always wants to be at that K value. So if some of this comes out, the reaction will shift back left to try and replace it. Shift left to try and replace it, which means that we would have an increase in H2 and a decrease in NH3 as we shift that direction. So this is down, this is up, this is down. Again, our K value stays equal. All right, I think I'll let you guys do these next two decrease ones. Same thing. You know, if I decrease some NH3, it's going to shift back to try and replace it. You know, if I pull some of this out, it'll shift back to try and replace it. So those will both go down with it. The K value doesn't change. All right, let's go to temperature. So this is probably the hardest one. Temperature is probably the hardest one. Our delta H is negative 92 kilojoules per mole. Remember, that is in the forward direction, it's exothermic. Forward direction is exothermic. So that means as we move this way, heat's being given off to the surroundings. Okay, it's endothermic the other way. So as we add heat in, it's moving that way. As we put heat in, it moves that way. So I always tell students, every time we add heat, every time we increase temperature, it always moves in the endothermic direction. Anytime we increase temperature, we want to make it so the reaction uses that heat up. So the endothermic direction is always using that heat up. So if we add heat, if we increase temperature, the reaction will always shift in the endothermic direction. Okay, if we make it colder, it's always going to shift in the exothermic direction to try and release some heat. Okay, and heat things back up. So an increase in temperature. So if we heat this, so we're heating it, it's going to move in the endothermic direction. Okay, it's going to move in the endothermic direction, which would be back. Remember, it's forward in the exothermic direction, so it's going to shift back. If we think about things here, we're going to have the effect of N2 is going to be, if we shift back, is going to be an increase. The effect of H2 will be increased because we're shifting back, and the effect of NH3 is going to be decrease. So let's think about our K. Our K is NH3's concentration over N2's concentration times H2's concentration right there. Well, right now, we are increasing this and decreasing that. So that is going to make our K value go down. We're putting a smaller number on the top and bigger numbers on the bottom of a fraction. That's going to make this decrease. We're going to have a decrease in our K value. Temperature is the only thing that changes the K value. That K value is a set value for a certain temperature. It changes with temperature. The reason it didn't change before when we were changing concentrations is, you know, say we increase this concentration, well, both of these went up with it, okay, because it shifted back that way to replace it. Where here, they're counteracting each other, all right? And this would only be true that the K value goes down for that would be based on the fact that this is an exothermic reaction going that way, okay? So a decrease in temperature would do the opposite things. So I'll let you guys put that one in there. Decrease would be all the opposite arrows. So again, an increased temperature, you always go in the endothermic direction. Increased temperature, go in the endothermic to try and use the heat up. Okay, use the heat up. And the K value does change. All right. Our last one's here. Pause you for 1 second. All right, want to get the reaction written back up there. So now we're going to increase pressure by decreasing volume. So this only affects gases typically. Okay, it only affects things that are gases. So pressure only affects things that are gases, but a lot of times we're dealing with gases. So if we increase pressure by decreasing volume, so decrease volume, increases pressure. Okay, so you think about this now, there's less space in there. Less space. So we always want to shift in the direction where there's less moles of gas. Okay, so when we increase that pressure by decreasing the volume, that means there's less space. We want to shift to where there's less moles of gas. Okay, now all these things are gases. All these are gases in this reaction. We want to shift to where there's less moles of gas. Well, this side of the reaction has 4 moles of gas. That side has 2 moles of gas. 2 moles of gas take up less space than 4 moles of gas. Remember, at STP, a mole of gas takes up 22.4 liters. So in this case, if we are increasing pressure by decreasing volume, Okay, increasing pressure by decreasing volume. The reaction will shift where there's less moles of gas. We have less space, so it's going to shift right. The reaction will shift right, which means that we're going to have a decrease in this, a decrease in this, and an increase in that. Now, you would think that would change the K value. Okay, you would think that would change the K value as we go there. But our K value will stay the same in that case. Okay, K value will stay the same. We'll go through a little discussion on that at some point in time about why that is. But that's a little bit longer topic as to why that does not change. It has to do with all of their pressures changing and the fact that things are squared and cubed a little bit as we go through there. And all their pressures change proportionally. Okay, so the pressures change proportionally. The overall pressure will change to kind of counteract what it was before, because we're now going from 4 moles of gas to 2 moles of gas. That the overall pressure will change accordingly, and our K value will stay the same. So temperature is the only thing that changes K value. Temperature is the only thing that changes K value. Just the opposite here then. If we increase volume, we want to make more moles of gas and have the gas be able to spread out and get back to where that K value was. So we would shift left, okay, which would cause an increase in that, decrease in that, but our K value stays the same. All right, last couple things. If we add an inert gas, meaning a non-reactive gas, like a noble gas. So we add a non-reactive gas, so no reaction occurs. We just add another gas in there that's non-reactive. That does nothing. Okay, the overall pressure might increase in the system. Okay, but there's no change. So everything stays equal if we add a non-reactive gas. And last thing, if we add a catalyst. So say there's a catalyst in this system. All a catalyst does is make us get to equilibrium faster. But we still get to the same equilibrium, the same ratios of them. So all it does is make us get to equilibrium a little bit faster, but we still get to the same equilibrium. So everything stays the same in that case. Have a good day. Hopefully that stuff makes some sense.